Today we'll look at section 7.3, linear algebra equations, linear independence, eigenvalues, and eigenvectors. There's a lot in here. So let's start with our linear equations. So of A11, x1 was an A12, x2, and we'll go all the way out to an A1n, xn, and this will equal some B1. And let's make that actually look like a B. And we'll fill all this in until we get down to AN1, AN2, ANN, BN. So we can rewrite this whole thing as AX equals B. X and B are going to be column vectors. A is going to be a matrix. So a way we could visualize this is that A is going to be A11 up to A1n down to AN1 with ANN. X is going to equal x1 down to xn, and B will also, give it a dead spot on the screen. There we go. B1 down to Bn. Now in the book, you'll see some notation, possibly in parentheses, A, then a line, then B. That's going to be the matrix with A and then B appended onto it. So it's going to be an augmented matrix. So if we have a homogeneous setup, then all of these B values are 0. If it's non-homogeneous, then some of the B's are not going to be 0. So now if our A inverse exists, then we can easily find X. It's going to be that. So in order to solve it, we're going to have to, and let's make sure that those are vectors. We're going to have to solve this system for X's. Now, when we do this, just like we did before, we're going to have a homogeneous solution, and we're going to have a particular solution. So we can say that we have our A times X sub H. That's going to be equal to 0 vector. Then A times X sub P, which is equal to B. And then our overall answer is X sub H plus X sub P. So now, with this, specifically with our homogeneous setup, if our inverse exists, then with what we have written here above, X is going to equal A inverse times the 0 vector, which is the 0 vector. So our overall x will just equal x sub p. If our A inverse does not exist, then we have either no solution or infinitely many solutions. And now, if we have the infinitely many solutions set up, we're going to have this situation. Oh, by the way, let me go back. With our set with our infinitely many, yeah, we can do it here. That our AX equals 0. So either our A is going to equal a 0 matrix, or X is going to equal a 0 vector. So we could have either of those, or maybe even both. So something's going to be a 0 if our A is not invertible. Now with our infinite many solutions set up, and take a B vector dotted with y is equal to 0 for all y such that A asterisk times y is equal to the 0 vector. And these should be vectors. And now this A with the asterisk is our adjoint, where we took the transpose and the conjugate of it. So we need this to happen in order to have our infinite many solutions. Otherwise, we have the no solution. And now what we get is X is going to equal xi, Greek letter xi, plus X with this little o. So this is going to say that this is our initial condition. And that's going to be our x of h plus our x of p. And those are indeed vectors, and so is xi. And we'll get to what all that is a little bit later. So in order to get into this, we're going to look at our linear dependence. So things are linearly dependent. So we're going to use some notation that we're going to have this x with the I on top. We showed that with our x naught before. And so what's going to happen is if we have a big matrix, this is going to be the ith column in that matrix. So this will be x, 1, I, all the way down to x, n, I, in our overall matrix of x11, x12, x1n, so we're picking out one of these columns, and it's going to be the ith one. So for our linear independence, we're going to say we have our x1. Oops, don't want parentheses there. And that should be a vector. All the way out to our xn. and actually they use K, doesn't really make much difference, such that there exists a C1, C2 out to CK that are complex numbers. So fancy looking C, they're complex numbers. So they can have the I in it, such that each of these C numbers is not 0. For some I that's going to be in this 1, 2, 3, 4 up to n. And we have C1 x1 plus C2 x2 plus our Cn xn equal to the 0 vector. So basically we have a linear combination where our C, at least one of the C's is not 0, but the overall thing is. This is pretty much what we had before. Last one, or next one, is our idea of linearly independent. So we're going to have the exact same setup for this, but almost. So it's going to be our x1, x2, so on. And back here, I should have had arrows on all those too, because they're vectors. Such that C1, x1 plus that's our Cn xn is equal to the 0 vector if and only if Ci equals 0 for all I in 1, 2, all the way up to n. So the only way that we can get everything to be our to be 0 is if we have all the C's equaling 0 as well. So next thing is that our looking at this x times c is essentially what we get. Matrix x times vector c is equal to the 0 vector, where x is our x11 up to x1n down to xn1 over to xnn, and the c is a column vector. It has our c's in it. So that's another way to represent our linear independence type thing. So we set equal to 0, but then it's a matter of whether or not the c's have to all be zeros or not. So with this, if our determinant of x is equal to 0, then C is not equal to 0, which means that we have linear dependence. So in this case, C could be something, but it might be something else. But still, it does not have that requirement. If our determinant of the X is not 0, or X matrix, then we know our C has to equal 0. So therefore, we have linear independence. Okay, so what is this determinant? So let's start off small with a 2 by 2. Our determinant, shown by our vertical lines, we do our crosses going forward and our diagonals forward, diagonals backwards. Diagonals forward, everything you hit on a diagonal gets multiplied, minus everything going backwards. That's for 2 by 2. For a 3 by 3, there's a few different ways we can do it. So I've often seen these two, the first two columns, get rewritten. And then we do all of our forward diagonals that we can do completely in there. Now, the way I learned it, it was kind of like Pac-Man. How whenever you go into one side of the screen, you automatically appear at the next. So for the way I do it is I go here, but then I disappear, but come out over here to finish it off. Now, either way, it's going to be C, then D, then H. So you get it. That's fine. The way that I was taught is a little bit more condensed if you can visualize it. If you can't see it, then by all means, draw the extra little bit. And then we have all the backwards ones. So we end up with AEI plus BFG plus CDH. Now the ones that are subtracted, CEG minus AFH minus BDI. And that's just be a written one. Now, other ways to conceptualize your determinant is technically what we do is let me rewrite. We choose one of our values in the top. So let's pick A. We're going to cross out everything in that row and everything in that column. And we're going to do the determinant on what's left. Then we do the same thing on the next one. Cross out row and column. Now, the thing is, though, we need to subtract here when doing this determinant, because our order gets, or our, things get reversed here. So notice how the D to I is a left hand going one, but over here it's a right hand going one. So it's a forward facing rather than backwards. So we have to reverse our sign there to get our overall plus minus is correct. Then we're going to redo it again. This time we'll cross out the C's, and it's C times the determinant of what's left. Now notice what we do in each of these. So we have an A times EI, got it, minus an A times FH. For the B, it'll be a minus a BDI plus a BFG. And then for our last one, doing our cross, a CDH minus a CEG. So there's a fairly basic setup and explanation of them. Whichever way makes the most sense for you, by all means, use that one. Now let's get into our eigenvalues and eigenvectors. So whenever we write this AX equals Y, where A is a matrix and B and Y, or X and Y are column vectors, this can give us a linear transformation that maps X to Y. And we can then also write this as AX equals, and let me write this out. And I'll draw my little arrows on each of these. As AX equals lambda Y, or excuse me, lambda X. So since we're going to get just another column vector, we're going to multiply it by something. Where this lambda is a scalar. So we want to be able to come up with a way to simplify this. We want to kind of quantify our A matrix into just a number. So the question is, how do we do that? And we're kind of doing something where we could take a matrix times a vector, and then we're going to multiply or transform it into just a scalar times that. Now, whenever we multiply our A times X, we are going to get a column vector as a result. So there's nothing illegal that we're doing about it. So with this though, let's then move things around. We subtract it over. Now notice they both have an X in it. So we cannot do just A minus lambda, because A is a vector, lambda is a scalar, and they don't have the same dimension. So we can't just do that. However, we can do a little bit of a fudge on this of having our lambda be the identity matrix. So this bit here allows us to do that subtraction. And so our setup is going to have non-zero solutions. If and only if, IFF, if and only if, the determinant of this A minus I lambda equals 0. So we are looking for this setup because we know that our x's are not all going to be 0. And if this whole a minus lambda I, or I lambda either way, times x does not equal the zero vector, then we cannot get an inverse of this whole a minus I lambda. So our goal is to find our characteristic equation. And let me just type it, it'll be easier. Now that's nothing new here. But the way we find it is we're going to take this determinant of the a minus I lambda and set it equal to 0. So we are specifically looking for lambda values. They're going to make this determinant 0. And we're going to use that to find our lambda. Now, what is an eigenvalue? It's going to be those lambdas that make this determinant zero. By the way, determinant is just a value, it's not a vector, so we don't need the our 0 there is just a 0, not a 0 vector. And then what is the eigenvector? It's the x vector that corresponds to our lambda that we just found. So that we can get our a minus I lambda times x equal the 0 vector. And we're going to deal with square matrices. So an n by n matrix will have or has n eigenvalues and n eigenvectors. So it's kind of like a polynomial that has a degree of n. You have n roots. We're going to have n eigenvalues, n, which then correspond to our n eigenvectors. So there's a correspondence between those. And we're going to get our eigenvectors from the eigenvalues. So after we solve for these eigenvalues, we're going to plug them back into the a minus I lambda, and we're going to use that to then create our actual vectors that we get. And both eigenvalues and eigenvectors can be repeated. So just like before, whenever we were solving the equations, we can have real distinct answers, we can have repeated answers, we can have complex answers. So we're going to get the exact same setup, and you are going to see similar results from what we're doing. In terms of seeing the e to the t pop up and the t, e to the something t, and then the sines and the cosines. We're going to see that also here. Now, the word eigen is, I believe, Dutch, but means proper or characteristic. So, which is perfect because we're using a characteristic equation. And it's the eigenvalue, our characteristic value, that's then giving us all of this. So, same thing, just in a different language. Now, with our going a step backwards, with our linear independence, is we're going to check to see if we have linear independence among our a couple of different vectors. So let's say our x1 is 1 to -1. Our x2 is 2, 1, 3. And our x3 is -4, 1, -11. And let's make that actually look like a -11. So like we said before, we're going to take our x vector times our c column vector, see if we can get 0. So essentially it's going to be a c1 times our x1 plus a c2, x2 plus a c3, x3. And then the whole thing is going to equal 0 vector. So what we want to do is make our augmented matrix. And then we're going to tag on the zeros. Then we want to use our row operations to try to get down to a simplified version so that we can come up with values for our C1, our C2, C3. So I'm going to recopy this because we're going to need more room. So we can add our row 1 and row 2. Excuse me, row 1 and row 3. And we can store that in row 3. Because that'll give us a 0 there. 2 plus 3 is 5. -4, -11, -15. 0. We can also take 2 row 1s minus a row 2 and store that in row 2. My arrow. So 2 times 2 is 4, minus 1 is 3. 2 times -4 is -8, minus 1 is a -9. Now for both of these, we can take 1/3 of R2, put it in R2, and 1/3 R3, and put that in R3. Excuse me, make that a 1/5 of row 3. So try to simplify these. And then we can take row 2 minus row 3 and store that in row 3. So from here, there's one more thing we can do. Let's try to get rid of, simplify row 1 a little bit. So we want to get each of these, so we just have 2 variables that we have to deal with. So if we take row 1 minus 2 row 2s, and store that in row 1. I'll finish off that matrix. That's not going to change. That's now a 0. And then 4 minus a negative 3 times 2. So that's 4 plus 6. Negative 4 plus 6, that's 2. All right, so now what we have here is a C1 plus 2 C3s equals 0. And C2 minus 3 C3s equals 0. So notice that both of these have C3s, so we can solve exclusively for, solve for our C1 and C2. That way we can have C3 as our controlling number. So C1 equals a negative 3 C3, oops, sorry, negative 2 C3. And C2 is going to equal 3 C3. So if you make your C3 equal 1, then C1 equals negative 2, and C2 is going to equal 3. So negative 2 x1 plus 3 x2 plus x3 is equal to the 0 vector. And these x's should be vectors as well. So right here, we've proven linear dependence, which we kind of saw back when we were doing our matrix manipulation, because we got a row of all zeros there. Actually, it really doesn't matter if all zeros there. That we have our dependence. But here it's showing that here is the situation, here's the values for our C's that we can use to add up to 0. So we don't need them all being our C values to be 0 in order to do this. So there's linear dependence, independence. Let's look at our eigenvalues and eigenvectors. So let's start with an example of our A. And we're always going to do A minus I lambda. So along the main diagonal, no matter what is in there, we're going to append a negative lambda to it, or a minus lambda afterwards. And now let's take the determinant of this. So if you want to rewrite, do our forward, forward, forward. So our determinant with A minus I lambda we're going to get a negative lambda times negative lambda times negative lambda plus 1 plus 1. Let's do our reverse. That's minus a negative lambda minus a negative lambda minus a negative lambda. So we end up with a negative lambda cubed plus 3 lambda plus 2. And we want this to all equal 0. So first important thing is to find something that works. And in this case, a negative 1 will work. So negative 1 plugged in is one of our solutions. So now we can do our synthetic division. Add down, multiply our number up here by whatever is down here, make it your new slot. Add down, then multiply, add down, multiply, add down. Okay. So from here, we can factor this into a lambda minus a -1, and then negative lambda squared plus lambda plus 2. But that's then going to factor some more. We can factor a negative out, and then it's a lambda minus 2, lambda plus 1. So our eigenvalues overall are -1, -1, and 2. So there are our eigenvalues. Next, we want to find our eigenvectors. So now we're going to go back up to this a minus I lambda and actually plug in these lambda values. So let's get a new screen. So we'll do, oops, here we go. Let's use -1 and something to go screwy on the computer. -1. And so we're going to do our row operations again to try to change this. And it's pretty easy that we can just subtract. And this is going to be our simplest form. So we know that C1 plus C2 plus C3 has to equal 0. And we're going to be able to find different ways for this to work. So we could have a -1, a 0, and a 1. We could have a -1, a 1, and a 0. We could have a 2, a -1, and a -1. So there's a bunch of different ways that we can set all of this up. But we're only going to be able to get 2 of these that are, after we find 2 of them, that are linearly independent. So they're not going to be multiples of each other. Any other one we come up with is going to be some linear combination of those 2. So let's use these first 2 just because they're the easiest. And by the way, if we do a -1 on this, multiply it, and then multiply this by a -1, and add them together, we get that third one. So our eigenvector for one of them could be -1, 0, 1. The eigenvector for another one would be -1, 1, 0. And there's nothing special about just those 2, just the first 2 I picked. There's an infinite number of combinations we could use for this. For the next one, we can do our lambda is equal to 2. So it's a negative lambda, negative lambda, negative lambda. Now again, we're going to have to use our row operations. So let's do row 1 plus 2, row 2, and then the same thing plus 2 row 3s. So we get zeros there. So that's a -3, and then that would be a 3. And then that's a 3, and that's a -3. So then these 2 will cancel very nicely, and we can simplify. And then we can go a step further. And even a step further. And we can make the C3 the same. We might make life a little bit easier. So changing this, it's a C1 minus C3 equals 0. Here's a C2 minus C3 equals 0. So solving those, C1 equals C3, which happens to also equal C2. So our eigenvector for this one, pick any value for one of those, we'll pick a simple form. So for this solution, and by the way, going back, those should be vectors. Our overall X matrix will be C1. And what do we say one was? -1, 0, 1, plus our C2, -1, 1, 0, plus our C3, 1, 1, 1. And so we've found our solution to the setup of the A we gave times our X equals 0. And based on the A's, that would be our setup. So that's it for our eigenvalues, eigenvectors. Last little bit of terminology is something called normalized. And when we talk about something being normalized, it's going to be an eigenvector which we know multiplicative constants C1, C2, and C3. Or C1, C3, or C3, because each vector will only have one of them. So it's normalized, we know what that constant is out front. An algebraic multiplicity is the multiplicity of an eigenvalue. So in the example we just did, for -1, the algebraic multiplicity was 2 because it was in there twice. For 2, the algebraic multiplicity was 1 because it was only in there once. And if we say it's simple, then it's some matrix A such that all eigenvalues have algebraic multiplicity of 1. So a simple matrix, every eigenvalue has the algebraic multiplicity of 1. So no repeats. Our geometric multiplicity is the number of linearly independent eigenvectors that an eigenvalue has. So this number is not always the same as the algebraic multiplicity. So it's going to have at least 1, but then the geometric multiplicity could be less than the algebraic. So even though eigenvalues in there twice, it might not have 2 linearly independent eigenvectors, and we'll see that later on. And then we'll look at how we're going to handle that. Last idea is called the Hermitian matrix. And with this, it's self-adjoint. So a way of looking at this is our matrix is equal to the adjoint matrix. So if you transpose it and take the conjugate, it's going to be equal to the original. So a way of looking at this is any ij value is going to be equal to the conjugate of a ji value. So it doesn't matter what's on our diagonal, because they're always going to be, they're not going to change in the flip. Well, actually, they have to be all real because they're going to be equal to the conjugate of itself. But then we'll have a d plus ei, and then here would be a d minus ei. Because whenever we do the transpose and do conjugates, then they're equal. And so here and here, and then here and here are also going to be complex conjugates of one another. So there's your general introduction to the eigenvalues, eigenvectors. We will get into these in a whole heck of a lot more detail later on.